Chapter 4 covers probability, with the first section focusing on the building blocks that we'll be using throughout the chapter. Just a reminder, the first section, 4.1, is a 1 or 2 paragraph summary of what we'll be covering in the chapter, and the first actual section is this one, 4.2. To start, let's go over some terminology. When we talk about the sample space of a problem, we're talking about all possible simple events. And when we talk about simple events, we're talking about outcomes in a problem that can't be further broken down. Applying it to a real life situation, flipping a coin has the simple events heads and tails. That's the full sample space. Those are the only outcomes that we can get when we flip a coin. Rolling a die has the outcomes 1, 2, 3, 4, 5, 6 that make up the full sample space. When you see this, capital P, it's talking about the probability. These would be events, right? So something like this down here, P with the A inside the parentheses means the probability of event A occurring. Other things you should know, there's something called the law of large numbers, which just says that larger samples produce more accurate estimates. If we flip a coin 10 times, we might get 7 heads, 70% heads. If we flip that same coin 100 times, we're going to get much closer to 50% heads, 50% tails. Rare event rule, the actual definition is here. Okay, but to put this in more understandable terms, let's say you're playing poker with someone and they're dealt a royal flush, which is the strongest hand in poker. Obviously, they win the hand because that hand can't be beaten. It can only be tied by another royal flush. So they win all the money for that hand. You play the next hand, they're dealt a royal flush again, so they win the hand again, and then you play another one and they are again dealt a royal flush. Right? The assumption is that this person is playing fairly, but the odds of being dealt 3 royal flushes in a row are so insanely small that it's much more likely that this person is cheating. Okay? And that's what the rare event rule really says. If we observe an event that's extremely unlikely to occur, its probability is extremely small. Okay? The underlying assumption that we're making, in this case, that the person is playing poker fairly, is probably not correct. As to what percentage or what probability we consider unusual, typically it's 5%, but that number can change based on the problem. Lastly, subjective probabilities. When we don't know anything about an event, we're just going to estimate it using our real-world knowledge about the problem at hand. Probability is always a number between 0 and 1, and those are inclusive values, meaning that probability can equal exactly 0. That means that that event is impossible to occur. If probability equals 1, it means that that event is certain to occur. When we write probabilities, we write them to 3 significant decimal places, or we write it as a fraction. Okay, and we should always write it as either a decimal or a fraction, or we can convert that decimal to a percentage, which is also acceptable. First example, find the probability that a randomly selected car in the United States will be in a crash this year. For a recent year, there were 6,511,100 cars that crashed among 135,670,000 cars registered in the United States. So for this problem, we just want to take all the cars that were involved in crashes and divide it by the total number of cars registered. When we do that, we get this decimal. Now, on one of the previous slides, it had mentioned rounding to 3 significant decimal places. What that means is when it says significant is that this 0 doesn't count. Okay, the significant decimal places start at this 4. So 1, 2, 3. Okay, would be up to that 9 there. And we're going to round it based on the 4th, which means that 9 gets rounded up, and we end up with our answer 0.0480. Okay, we also could write it as a percent, 4.8%. Example 2, below are test results from experiments with polygraph instruments. Polygraphs are just lie detectors. Assuming that one of the 98 test results summarized is randomly selected, find the probability that it's positive. All right, so anytime you have a table like this, the first thing we want to do is add up all the rows and columns. So if we look at this first row here, okay, and just add across, 15 plus 42, we get 57. Do the same thing below it, 32 plus 9, 41. Okay, those two numbers added together give us 98, and that's what we would expect to get based on the number up here in the problem. Okay, do the same thing with the columns. So this no column gives us 47, and this yes column gives us 51. Okay, these two added together, 47 plus 51, also gives that 98. All right, so we want to find the probability that it's a positive test result. Of these, positive is this number right here. There's 57 positive test results because everything on this line is a positive test result. That's out of 98, 57 out of 98, 0.5816, 3 significant decimal places, round based on that fourth one, okay, 0.582 or 58.2%. Example 3, find the probability that when a couple has 3 children, they will have exactly 2 boys. Assume that boys and girls are equally likely and that the gender of any child is not influenced by the gender of another child. So first thing to figure out is how many possible outcomes do we have for the births of 3 children? In other words, what's the sample space? So each child, there's 2 possible outcomes. We can have a boy or a girl. Okay, that's for the first child. Okay, and then we have a second child. There's 2 outcomes. Third child. Okay, boy, girl, boy, girl, boy, girl. Right, so altogether we have 8 outcomes. Basically, we're just doing 2 raised to however many we're having. So 2 to the third power. Okay, it gives us 8 there. All right, so now once we know that, okay, we're going to take that number and we're going to cut it in half. Okay, so we get, cut it in half and we get 4. All right, so 4 males and 4 females. What we're doing now is we're writing out the sample space. Okay. After we write 4 males, 4 females, we cut it in half again. Okay, and we'll follow it up with 2 males, 2 females, 2 males, 2 females. All right, and we keep cutting in half until we get down to 1 male, 1 female, 1 male, 1 female. Okay, so we started with 4. Okay, the reason we started with 4 is it was exactly half of how many we had. All right, and then we cut that in half, then we had 2 at a time, then we cut that in half, and we have 1 at a time. All right, so this is our full sample space. There's 8 ways that we can have 3 children, ranging anywhere from all males all the way to all females. Okay, so in this situation, for example, we have 2 boys, then a girl. The one underneath it, we have a boy, then a girl, then a boy. All right, down second to the last, we have 2 girls, then a boy, etc. All right, so the actual question is saying, what's the probability that they have exactly 2 boys? Okay, so this here has exactly 2 boys. This here has exactly 2 boys. This here has exactly 2 boys. All the rest have something other than 2 boys. So 3 out of the 8 have exactly 2 boys. That's 0.375 or 37.5%. Okay, the tricky part of this problem is coming up with this, writing the sample space for the birth of 3 children. Example 4, we have this question about Kentucky Fried Chicken. All right, they were asked, would they gain or lose business after eliminating trans fats? 1941 said that they would gain business. 1260 said that it would remain the same, and 204 said that they would lose business. We want to find the probability that they would gain business. First step is we have to find the total sample size. Just add those all together. We get 3405. Right, divide it. 1941, which is the percent or number was said they would gain business, and we get our answer. 0.56987. Remember, 3 significant decimal places rounded based on that fourth, 0.570. Lastly, we have a number of problems about coins. What's the probability that we flip a coin and get heads? Simple, 1/2. All right, part B, what's the probability that we flip a coin twice and get heads both times? Okay, so the first coin needs to be heads, right? Then we flip it again, we get heads again. For problems like this, we're going to multiply those 2 probabilities, so we end up with a total probability of 1/4. Flip a coin 3 times and get all heads. We're just expanding this out to a 3rd time, so heads, heads, heads again, 1/2, 1/2, 1/2, gives us 1/8. All right, and then D, flip a coin 3 times, get tails, then heads, then tails again. All right, if we think about this, it's really exactly the same as we had in part C. All right, 1/2 chance of getting tails, 1/2 chance of getting heads, 1/2 chance of getting tails again. All right, so 1/8.